Okay, so we're going to continue working in Module 4. So this will be our second session on Module 4. And if we look in our learning plan here for Module 4, you're going to notice that we are working out of a handout instead of the textbook, okay? So, so it happens to be a chapter out of a previous textbook that I worked out of. So that's going to be the PDF here. I did print mine off and it's going to be underneath the camera. And then you'll notice that we're going to be working the examples as we see here, and they are part of a handout called Guided Notes for this module. We've been filling some things as we've been going along, but there's also spaces to put the examples in as well. If you don't print this off, that's okay. Just take good notes and then hand all of this in at the same time. We are going to be looking at problem 4-5, and this is found on page 70 in the chapter 4 handout that we see up here. And I'm also going to pull it up underneath our camera. Problem 4-5 is on page 9 in our guided notes. So I'm going to go over there and look under here. Okay. Just a little bit closer. Okay, now, before we go too far, it has been a little while because we had our assessment in between here from the previous 3 modules. And before we got to page 9 here, on page 8 in our guided notes, we had a little bit of a review. So I know we filled this out the last time kind of at the end of class, but let's just take a peek here to kind of bring these same concepts back up in the front of our minds so that as we work on our next problems here that we're all set, okay? So you'll notice here at the top, we did introduce a new convention. Our new convention adds the rotation. So we were talking about moments and how moments are forces that are offset from a point that are going to cause a rotation or induce a rotation on the body. So we need to identify, because we're going to be assigning positives and negatives to the rotation of those moments. We have to decide what's positive and what's negative. So according to our convention, we're going to have counterclockwise rotations as being positive, So this is going to be the complete and final convention that we're going to be using from now on, okay? Now, as we look here, the sentences that we're filling in, it says all forces pointing up and to the right are considered positive, and all moments that are counterclockwise are also going to be positive. Now, as a review, moments are going to be the tendency of a force to cause a rotation about a point, okay, or an axis. Sometimes we sum moments around axes. The magnitude of that moment is going to be found by multiplying the magnitude of the force times its perpendicular distance from the point that we're summing our moments about. Okay, so those are things that we've been practicing, kind of getting used to. Now, says write the moment equation. The moment equation is going to be, we're going to sum. So we use that capital sigma to signify that we're going to be summing something. So we're going to sum capital M the moments. And then the sub, I have a 0 right now, but it can be moments around point A, point B, point C, but we always want to identify what we're summing around. So sum the moments around point, blah, blah, blah. Equal to, and then notice out front here of this parentheses, I have a plus or a minus. That is going to be dictated by the direction of rotation. When we're summing moments, or I say when we're in moment mode, we're looking at the direction of rotation that the force is causing about the point that we're summing around. So you'll notice that in parentheses here, then I take the magnitude of the force times the perpendicular distance, okay? So force times distance inside, and then outside is going to be the direction of rotation. The important thing here to remember is that a positively directed force, depending on what side the point is that we're summing around, can cause a negatively directed moment, meaning it could cause a clockwise rotation and it would be negative. So that when we're summing moments, we're always looking at just the rotation. Just the rotation, not if the force is up, down, left, or right. That's summing forces, okay? Then units that we're going to see for moment, because it's going to be force times distance, those units are going to be newtons times meters, or pounds times feet, or kips times feet, or pounds times inches. So always force times distance. The sign out front of a moment is always going to signify its direction of rotation, not the direction of the force. And again, Clockwise is negative and counterclockwise is positive. So any questions here? Kind of remember that stuff that we talked about? Ish?
Real quick,
Yes.
for, like, pound feet, is there any difference between pound feet and foot pounds?
There is not, except torque. When we talk about torque, and it is important to mention that. So I'm glad you brought that up. So torque a lot of times is going to be pound feet, pound inches, right? They do the distance first. And no, it is the same. And torque is actually actually also going to be calculated using the force times it's what we call the radius to the center of rotation. Now torque fundamentally is different than a moment because torque is going to be something that is intentionally rotating about an axis, okay? Moment, on the other hand, we're going to notice that it's going to be in relationship to things that probably aren't supposed to be rotating, but there is a rotation caused by offset forces. So moments, for instance, in beams are not meant to rotate, okay? But we need to find out what is the tendency of rotation because of that force that's offset from a point. So that's why we call it moment. And you're going to notice that we always use pound. We always use the force first and then the distance. So there is no difference, but in the application, okay, in the application. So when you guys talk about torque in strength of materials, okay, you're gonna, you know, kind of revisit this. You might even ask, like, how is that different than moments? So then you'll talk about it again. And again, it's fundamentally the same when we look at force times distance, but the application is different. The intent is different. Okay, good. Any other questions before we move to problem 4.5? Okay, all right, cool. Cool. So let's look at page 9. Okay, page 9 in our guided notes here is looking at problem 4.5 on page 70. So like I said, I have mine printed out here. This is page 70 in the handout. And number 4.5 is right here. So what I'm going to have you do is take a couple minutes to draw the diagram that you see right here. And what we're going to do is we're going to determine the moment of the forces shown about points D, E, F, and G. Okay. And there's plenty of space here. So don't make a small little diagram. You've got all this space right here to make a diagram. And I'm gonna do the same. Just gotta grab my. Now you don't have to draw it to scale, just kind of proportionally, right? So this is 3 units wide. Where go my? So as you're completing your diagram, like I said, it doesn't have to be perfect. Mine's obviously not perfect. But what you want to do is you want to add all the points that are there. You want to identify that each one of these squares is 1 meter. Okay, and then what I'm going to have you do right away is you'll notice that our next step is to break any forces that are not on the X and Y axis into their X and Y components. So go ahead and draw their components. I'm gonna kind of do it on the side here. I'm not gonna bother you with talking it through, but you can peek, you know, at what I'm doing to see if you're on the right track. So I'm gonna break my 20 kilonewton force, which is at a 45-degree angle. Does not look like 45 degrees here, but since this is a 1x1, this would be a 45-degree angle, which is the same line of action for that 20 kilonewton force. So we need an X and a Y for that one. And then also for the 25 kilonewton, we need an X and a Y for that one. So you should be getting AX Well, I'm calling it AX, I'm sorry. My AX, I called the 25 kilonewtons A, just to get a variable in there for AX and AY. So that horizontal component is gonna be 19.15. It would be going to the left. You have to use the sign of 50 for that one because the 50 is located here to the Y axis rather than the X. And then the Y component for that one is going to be the cosine of 50, and that's gonna be 16.07 kilonewtons. The BX is that 45, I called the one up in the corner here, the 20 kilonewtons, I called that B, 45-degree angle, so cosine of 45 times 20 kilonewtons, you've got 14.14 kilonewtons. And then because it's a 45-degree angle, the Y component will also be 14.14 kilonewtons. You don't have to show the work for that. It's the same, as we know. All right, any questions there? You guys get the same answers as me as a confirmation? Okay. Okay. Then what we're gonna do is we are going to turn the page, okay? We're gonna turn the page. And like I have my components here. We'll come back to this because we'll be referencing that when we do our moments. So I'm sure I'm going too fast. Got it, everyone? Okay, so now we're going to turn the page on page 10. Now we want to sum those moments around the points identified in the problem. So going back over here, the first point we're going to do is going to be about point D. Okay, about point D. So I'm going to say, I'm going to go over to the right here just because I know as I sum, it gets a little long. So sum my moments around point D is equal to, and then we're going to start summing. So I'm going to go back over to this side right here, and I'm going to put my finger on D, okay? Put my finger on D. And I'm going to work around in a clockwise direction here, and I'm going to start with AX, what I'm calling the AX. And I'm simply going to pull in that direction while I hold my finger at D. You'll notice it causes a rotation, so I'm going to include it in my moment equation. So I'm going to take its magnitude times its perpendicular distance. So you'll notice that it would be 1 meter times 2 meter. And then here's my perpendicular 90 degrees to that. Now, just want to reiterate again, I cannot use the 25 as a perpendicular distance because it's more than 90 degrees back to my point D. If I wanted to use the 25, I would have to extend this back and find that perpendicular distance to that line of action, okay? But if I can just use my X's and Y's, I've got natural dimensions built in, if you would, okay? So that's why breaking these into X and Y's become really convenient. So we're gonna take the magnitude of our AX, multiply it by 2 meters, okay? So looking down here, our AX is 19.15 kilonewtons. So going on the other side, 19.15 kilonewtons times 2 meters. So this is, I'm going to call this AX, okay? You don't have to label those, but just for a point of reference, times its perpendicular distance. Now out front, I need to give it a sign. So I'm going to go back over here. I'm going to put my finger on D, and I am going to rotate. It's rotating in a counterclockwise direction, so that means it's going to be a positive value. Now, technically, you don't have to lead with a positive here. I'm going to intentionally put it so that you can see that that is counterclockwise rotation of that moment. But if you left it alone at the beginning there, that's okay. All right, that's okay. All right, so that's our first one. Let's go back, put our finger back on D, go back to A here, and we're going to pull in the direction of AY. And you'll notice that it's not causing a rotation because if we pull it back along its line of action, it goes right through the point. So there's not going to be a moment generated. So we don't include it. So you don't need to say AY times 0. Just go over it. We don't include it at all. Now we're going to go up to B. I'm going to start with the X component. So I put my finger on D and I pull in the direction, and sure enough, my paper rotates. So I know I'm going to be including it. Now BX, it's going to be the magnitude of BX, but what's its perpendicular distance? Now remember, per the principle of transmissibility, I can move these forces along their line of action. And I want to try to find, if you would, a radius, okay? So I like to pull it back along its line of action until it's in line, perpendicular 2D. So I could push this all the way back along here and my perpendicular distance is gonna be 4 meters. Do you see that? 4 meters. So I'm gonna take my BX, which is 14.14 kilonewtons times 4 meters. I'm gonna leave a little space in between because I know I'm gonna have to put my sign in there. Kilonewtons times 4 meters. Make sure you put your units in all phases. And going back, I'm gonna put my finger back on D and I'm gonna pull and it's going in a clockwise rotation. So that means I'm gonna put a negative out front. Negative out front. So I want to show you something here. That force is going to the right. That force is in a positive X direction, but causing a negative rotating moment. That's why it's important to put the moments in parentheses and give the product a sign because it's based on rotation. So this one is clockwise. Okay. Any questions on that? All right, let's go to the next one. Put our finger back on D. Now we're going to pull in the direction of BY, causing rotation. Now we're going to pull BY back along its line of action. So we can do that very same action. If we place BY right here, same net effect on the body, and its perpendicular distance is going to be 2. Okay, 2 meters. So BY we know is 14.14 kilonewtons, and the distance is going to be 2. Okay. And then lastly, before I leave that, I need to put a sign out front. Go back to B, pull, and it's going to be going counterclockwise. So that's going to be positive out front. Okay. So this was BX, this was BY. I'll just give that as a reference. Okay. Now I do have one more, so I'm going to have to turn the corner here. And I've got 50. Okay, I'm going to put my finger on D, pull on 50, causes rotation, so it will be included. So I'm going to take my 50 newtons as my magnitude, and I'm going to determine its radius or its perpendicular distance. If I pull it back, I can do that very same thing here, and it's going to be 1 meter is going to be the distance. Okay, so 50 times 1 meter. So 50 kilonewtons times 1 meter. And then out front, my sign is going to be clockwise would be negative. There we go. Okay. And now as we look, there are no other forces to include. So we're simply going to do our multiplying, adding, and subtracting, and our sum of our moment around D. I don't know the number. I'm gonna wait for you guys. I don't have my calculator and I hate using my phone, so I'm gonna wait. Let me know when you get a number. I'll watch the chat box. You can put it in here too. Yes, what do you got?
39.9.
That sounds correct. Negative 39.98, and that's going to be kilonewton meters. Correct. Anybody else? Just a confirmation. Yep, Jack got the same thing. Awesome. Thank you. Thank you. Thank you. All right. 1 down, 3 more to go. Let's do another one together, and then I'm going to let you guys do the last 2 independently. Okay. So our next point, I think, is going to be, we'll pick E right up in the corner here. So put our finger on E, and I'm going to, again, work in a clockwise direction. So I'm going to go over to B first. So I'm going to start on E. I'm going to pull in the direction of my Y. You'll notice it causes rotation. So I'm going to take its magnitude times perpendicular distance, which is going to be 2 meters. And as you can see, it's going to rotate counterclockwise. So it'll be positive out front. BY is 14.14. So I'm going to sum my moments around point B equal 14.14 kilonewtons times, did I say 2 meters? 2 meters. And it was going counterclockwise, so positive out front. So this was BY. Our next one, as we go, some of the moments around E, not B. I'm gonna pull on my B, X component does not cause rotation, so we're not gonna include it. We pull it back along its line of action, it goes through that point. No moment generated. But now if I go down to my 50, that causes a rotation. So the magnitude is gonna be 50 times its perpendicular distance. We're gonna pull it back along its line of action. Its perpendicular distance is gonna be 3 meters. So 50 times 3 meters. And then the direction of rotation counterclockwise will be positive. So we can say positive 50 kilonewtons times 3 meters. Okay. Next one. Put our finger on E. We're going to pull in the direction of AX causes rotation. Okay. AX magnitude is 19.15 kilonewtons. Perpendicular distance from E, 2 meters. And then the direction of rotation, clockwise, it will be negative out front. So 19.15 times 2 and a negative out front. Negative. Two meters. And this is AX. Then, as we go on E, the last force is going to be AY. It pushes right through E, so there's not going to be a moment there. So the last one was our last force. So we would have 1, 2, 3. So we can go ahead and add and subtract here and find the moment around point E. Let me know what you get. Can't believe I forgot my calculator. It's so weird. There you go. I got that same thing. It took me a little while. 139.98 kilonewton meters. Thank you, Jack. I appreciate it. Confirmation from anybody? Great. Great, great, great. Now, something I didn't mention, you'll notice that the top one says negative 39.98, and this one that we just did is a positive 139.98. What do you think the difference is between these two? What was that? What is it? 100? Well, yeah. Well, yeah, the difference is 100. I'm asking, I guess I should ask more directly. Why is one negative and one not negative? You're right, the difference between the two. Exactly. What you said. This is a math class. Jack, go ahead. Yeah, so if we go back over here, it's determined by one of them is going in a positive rotation. One of them is going in a negative rotation. So that means that our moment around D, the tendency of those forces is to create a clockwise rotation, and the tendency around E is going to be a counterclockwise rotation. Okay. All right. So we've got 2 more points to do. We have F and G. Go ahead and sum the moments around F and G, and we'll compare. Try to line up now. Oh, thank you. Oh, you got 49.52, huh? Jack? I have to check. Times 3. Maybe you held a decimal or so. Oh, you did get 49.35. Okay, all right, good. Thank you. And then in the room, if there's any confirmations as well, that'd be awesome. Like I said, I don't move as quickly and I don't know, my phone is just, I don't know. Do you guys feel that way too on your phone? Real calculator, like pressing the buttons, it's just like such a big difference. Doesn't feel like it should be, but it just kind of is. So I really like this exercise because it gives us a lot of practice doing the rotations, figuring out the distances, pulling forces back along their lines of action, getting those perpendiculars, you know, and the force times, and then really paying attention to the signs, clockwise, counterclockwise, and such. Hopefully this practice is helping this kind of, this is one of those things, at first it feels a little weird, but by getting this practice and being, you know, just kind of diligent about it, it starts to sink in and it gets easier. By the time we're done here in module 4, you'll be like good with the moments. Did anybody get the same number as I did here, the negative 130.61? No? I did it twice on my numbers. I looked at my numbers twice. You got it, Jack? Okay, good. Thank you. Any questions about the moments that we see here? All right. Okay. Are we ready to shift gears or does anybody want to see this up here for a little bit yet? I don't want to rush too fast. Looks like everybody in the room seems to be ready to move on. Okay, so then let's turn the page. Let's go to page 11. Page 11. So I'm going to zoom out a little bit. On the top of page 11, we're going to a new section, still on page 70, but there's our next column here. It says resultant of parallel forces. Okay. Now the resultant R of a parallel force system must have the same equivalent effect on the body as the original parallel system of the individual forces. So thinking back to when we're in module 2, we wanted to know what was the resultant force of a concurrent force system. That's where we had a common point, whether it was the point of application or a point of intersection, okay? But we wanted to know what was the one force that would replace 2 or more forces and have the same net effect on the point, okay? Same net effect on the point. Christian, did you need me to go back? Oh, no problem, no problem. I'm sorry. Just always stop me before we move on. I try to ask, what do you need to see?
Just the bottom. G.
Yep.
Just checking. Values.
19.15 times 2 minus 1607 times 3 minus 14.14 times 1 minus 14.14 times 4. Okay. And then 50 minus 50 times 1. Okay. Yeah, don't feel bad about having me wait to move on. All right. Okay. All right. So thinking back about resultants, we want to now place a resultant that it's going to have the same net effect on the body as the individual forces, but this time they're not sharing a common point. They're not sharing a common point. So if we look at figure 4.9 on page 79, it's up on the top here, okay? As we look, this is what we call a parallel force system. Now, I'm not crazy about the way they show it to me. Why not just show it, you know, vertically, but they have it going off at an angle. But all this says or the impression here that we get is that these 4 forces, F1, F2, and F3, will never intersect, right? We can push them along their line of actions for affinity and they won't intersect because they're parallel. But if we want to find one force and place it along this line, where would we place it? That's what we're really trying to find. It's like we want to do one force instead of three. And then we want to make sure that we put it in the correct place so that it would have the same net effect on this body. Okay, so you'll notice that we're looking at point O, and the distance, the perpendicular distance of F1 is going to be its corresponding radius or distance 1. And then if we find the moment that this force 2 or the rotation it would want to create, then it would be multiplied by R2 or its distance, its perpendicular distance 2. And then the same thing for force 3. This would be its perpendicular distance, and then this would be its radius. So we would find the total moment that those three forces cause about point A. And then we're going to take our resultant and we're going to figure out where along this line is it going to have the same net effect as those. And we're going to call its radius R bar. R bar. It's just kind of how they chose to call it. Okay. So what we want to do is we want to go back to page 70 and we want to write down a couple key equations here. So I'm going to tell you which ones we want to do. All right. So in our section right here, the first one we're going to write down is we're going to sum our forces, and they could be in the Y direction, the X direction, or along like they see here, like at any line, but they're going to be parallel forces. And we are going to say that's equal to our resultant. So we're going to compare it to our convention. So if they're all vertical, any of the up forces are going to be positives, any of the down forces are going to be negative, and then the net effect is going to be equal to our resultant. Okay. The next thing we want to keep in mind is that we are going to sum our moments about, in this case, on that next illustration, it's 0.0. And we're going to say that's going to be equal to, and we're going to look back. We're going to put our finger on 0. It's going to be F1 times R1. Okay. F2 times R2 and F3 times R3 corresponding to each one. So we're going to put out front here F1 times R1. And then it's going to be plus F2 times R2, not R bar, R2, plus F3 times R3, okay? And whatever those magnitudes would be, we would take the force times the distance, the force times the distance. And if there was more forces, we would continue to figure out and add to our moment equation here and keep summing up however many moments there are, multiplying by their corresponding perpendicular distance back to the point we're summing around, okay? Now, when we want to place our resultant, we want it to have the same rotation effect, and we're going to take this resultant times this radius. So once we know what the total moment is of the individual forces, we can also set that equal to the resultant times its R bar. Okay. So now our process is going to be, we're first going to determine what the magnitude of that resultant is. And then we're going to sum the moments to determine what is the rotational effect of those forces on that body at their individual distances. And then using this value right here, we're going to put that number in there. We're going to take this number and put it there. And then we're going to solve for R bar. That's going to be our process that we do. Does that make sense to everybody? So these are going to be kind of our three key steps / equations that we're going to do. Now, the goal of these problems is always going to be determined first what that resultant is. What is its magnitude? That's that right there. And then we need to find out where to place it. So we first need to determine what is the rotational effect of those individual forces at their distance away from that point we're summing around, and using that value to solve for the R bar. So it has the same net effect on the body as those individual forces. Okay. So steps. When we do these problems, number one, we're going to have to draw a free body diagram and our free body diagram and add our convention with the rotation now. Then we're going to determine the resultant by summing those moments in the direction that they are found. Determine the moment generated by those individual moment or the individual forces. Determine the placement of R bar for that resultant. And then we're going to draw a final diagram showing our resultant and our R bar in relationship to the point that we summed around in step number 3, which is this one right here. Okay. So as we turn the page to page 12, we're going to look at example 4.4 on page 71. 4.4 on page 71. So it says for the parallel system shown that's acting on this rod, okay, determine the resultant or the equivalent force. Now determining the resultant, that's the magnitude, but remember we also have to determine where along that rod do we want to place that resultant in order to have the same net effect on the body as the 3 forces that are currently on there. Okay, so first things first, we're going to draw our free body diagram. Okay, so that's what we see here. So go ahead, draw your free body diagram and add your convention. Force A, B, and C. 6 meters. 10 meters. Now, once we have our free body diagram and our convention in place, make sure that you add all of your forces, labels, and distances. We want to find our resultant force. Okay, that's the second step, I should say. So first step is diagram and convention, and then we're going to do our resultant. So now notice that all of our forces are in the Y direction. So we're going to sum our forces in the Y, and that's going to equal our resultant. So we're going to start by saying exactly that. Sum forces in the Y equal to the resultant. And then we're going to sum our forces in the Y, and that's going to be our resultant. So as we look here, according to our convention, we're going to have a negative 10 kilonewtons, a positive 12 kilonewtons, and a negative 25 kilonewtons, right? So we're going to write that. So negative 10 kilonewtons, positive 12 kilonewtons, minus, 25. Okay. It's going to be equal to our resultant. So now adding and subtracting those, so that's going to be a positive 35 or a negative 35 plus 12. What's my number? Negative something. I'm not good in my head. I'm really calculator dependent. Minus 23. Is that right? Sounds correct. 23. Thank you, Josh. And Jack. Now, keep the sign. All right. There's a little note there. Keep the sign. It'll make a little bit more sense later. Now, the next thing that we're going to do, this is our magnitude of a resultant. So we're not done because now we're going to have to place that resultant somewhere along here. And we're going to have to figure out this so that it has the same net effect on the body. So for instance, I'm going to do this. I'm just going to draw my resultant, something like this. Okay. And I'm going to put this little squiggly because it's an equivalent load. And I'm going to say 23 kilonewtons. Okay. That's my resultant. And what I want to find now is how far away from point A is this going to be, or from that left side is this going to be? That's where we're going with this. Like we now know the resultant, but where do we place it? Okay, where do we place it? So to do that, to have the same net effect on the body, we need to determine what is the moment that the individual forces cause so that this has that same effect. Now, we get to pick the point that we want to sum around, okay? And I'm simply going to pick point A. Now, even though that force is going through there, that's okay, all right? Because from point A, we still have two other forces, and we're going to determine what is the moment caused by those two individual forces. And then we're going to use that to find our R bar. So determine the moment generated by the original forces. So we're going to sum our moment around point A. Now you could pick around B or C, but A is just on the left-hand side, and I always kind of tend to start there. Is going to be equal to, so I'm going to go back up here, and I'm going to put my finger on A, and I'm going to rotate the 12 kilonewtons times perpendicular distance of 4 meters. And then the rotation is going to be counterclockwise. So that's going to be positive. And then I've got one more force. Put my finger back on A, pull in the direction of C. That's going to be 25 kilonewtons times the full distance, 10 meters. And the direction that it rotates is going to be clockwise. So we're going to put a negative out front. Okay. So when we sum our moments around A, tell me what you get. Oh, Williams got it. Negative 202. I heard it in the room as well. Is that what you got? Jack got that? Okay, negative 202 kilonewton meters. Kilonewton meters. Oh, Josh got it too. Awesome. Thank you very much. Really appreciate that. Keep your sign. Hold your sign here, okay? Hold your sign. All right. All right, are we ready to turn the page? Now, we're going to go to page 13. Kind of put this up here, and we'll go down here in case somebody needs to write that yet. Step number 4 says determine the placement of R bar of our resultant. So let's go back a page. Okay. On page, isn't that page? Oh, was that page before here? On page 11, these were our 3 equations that we looked at. We already did sum the forces to figure out the resultant. We just did the moments to figure out the total moment due to the individual forces. And now we're going to use this equation right here. We're going to say sum of the moments around A, it's going to be equal to R times R bar. So on step number 4 here, that's what we're going to write. Sum the moments around A is equal to R times R bar. Now, from our previous step, from step number 3, we know that the sum of the moments around A is equal to negative 202 kilonewton meters. That's what's going to go right here. So negative 202 kilonewtons times meters. Put your units in here. It's going to be equal to our resultant, the magnitude of our resultant. We figured that out in step number 2, negative 23 kilonewtons. Negative 23 kilonewtons. And then our unknown variable is R bar. So now we're, Josh, you're ahead of me. That's good. I like it. So now we're going to solve negative 23 kilonewtons on this side, right? Our kilonewtons cancel and our negatives become positive. So as Josh already figured out, we've got 8.78 meters are left. Notice we didn't cross out meters here. Is going to be equal to our R bar. And as I remember, that is the correct answer. So you should be getting that as well. Now, couple things that we see here. You'll notice that we kept the units in all phases of the problem so that we could cancel out. And what we don't have left over are units for distance. We are expecting units for distance for R bar. So when that happens, You know that you set up the problem correctly. This way you don't just magically put the units at the end and like hope for the best, okay? We actually have set this up and we have cancellations appropriately. We have meters there and we can be like, yes, I must have set that up correctly because I'm getting units of distance for an R bar, okay? So that right here is why I have you guys do that, right? Chris?
We get like a different answer if we put the sum of all the forces with like the point B or point C.
You would get a different moment and you would get a different answer for the distance, but so if we go back over here, that's a great question. So what Chris asked was, let's say I sum my moments around B, okay? Would I get a different answer? You would get different numbers, but the placement would still be then from here to here. Yeah, that would still hold true. It would still have the same net effect. Yeah. Okay, good question. All right. Now, the very last step, we can put a box around this. The very last step is, it's nice that we got R bar. It's nice that we got R. Now I want you to draw a diagram and show me what those answers mean. Okay, so what we're going to do is we're going to redraw that rod from A to C. Okay, A, C, and then I think B was, how far was it? It was closer this way. B was here, okay? And now what we want to do is we want to take that 23 newtons, okay, 23 newtons, it's pointing down, and we want to draw it approximately 8.78 meters to the right of A. Okay, and we're coming from A because that's what we took our moment around originally. It has to come from that point. So this was 10 total. So our resultant then would be somewhere around here-ish. Okay, R is equal to 23. Do not write negative 23 here because the negative is the pointing down. That's our direction. It's going to be kilonewtons. And then from here is going to be our R bar is equal to 8.78 meters. Now, a double check here. If I put my finger on A and I pull in the direction of my resultant, it is going to cause a clockwise rotation. If I go back to where I summed my moment in step number 3, is that consistent with my total moment around A? Jack says yes. Why? Yes, this is a clockwise rotation because of that negative, right? So when I go over here, it has to have the same net effect. So now if I take my resultant and I rotate, it's rotating clockwise as well. See how that works? It's so good. Who's excited about like statics? Is it like totally your favorite class like right now? It has to be. I mean, I can't imagine anything being better. Maybe hot processes, maybe. Definitely not calculus. Can't be better than this.
So if you do this for topics.
Totally this, Christian.
Yeah.
You're not feeling
Fair
this.
enough, yeah.
Good. I'm glad you're not feeling this. Okay. All right. I'm just kidding. I know it's one of those subjects. It's kind of dry. I don't know, liven it up a little bit. All right. Any questions on the process? Let's just kind of review. Diagram, resultant, moment of the individuals. And then we find our R bar by setting that moment of the individuals equal to that resultant times its distance away. And then we're going to create a diagram. Okay. All right. Now, let's take a peek at where we're at here. So 13, 14. Okay. What we're going to do is this is going to be a second problem that we do like this. But instead of working out of here, would you guys be upset if we did one of your homework problems instead? I didn't think so. Anything but calculus, Jason says. Oh, so it's just statics because it's not calculus. Right now, it's your favorite. No, actually statics, I'm not gonna lie, when I was in your shoes, was my absolute favorite, And it's my favorite class to teach as well. I don't know if you can tell. Kind of, it's my favorite. All right, so the first two problems is summing moments around points. So 1 and 6 are gonna be kind of the first section that we just got done with. The problems that pertain to what we're looking at right now are on page 72. It's 4-8 and 4-10. So let's take a peek over there. And that's going to be in our chapter, not in the e-textbook. It's going to be in our chapter. So we're going to go to page 72. Okay. 4.8 is up here. We've got, it looks like 4 wheels are loaded as seen here. So there's a 1.5 kips and then the rest are 5 kips or 0.5 kips. We want to find the resultant and locate it to have the same net effect. And you just really are just going to put a line through these, you know, starting at A to B, and it's going to be similar to the last one we did. So 4 parallel forces in this case. The other one that you have is going to be problem 10. And it is actually the illustration up here, which is the truss. Now, what I want you to do is ignore the truss. What you basically have here is just a line with a couple forces that are supported at A and B. That's it. All right. So the line starts at A and ends at B, and you've got 3 forces in the middle. Don't let the truss make it feel more complicated than it is. It's not. And we want to find the resultant of those 3 forces along that line between A and B. So as you look at these two, is there any one that we would want to do either 4.8 or 4.10? Hold on, Josh, I'll answer that in just a second. So 4.8 or 4.10, any preference between the two? No? Then let's do 4.8, okay? Now, Josh asked me right now, he said, do we skip problem 4.9? Because that's found on page 14 in our handout. You can say yes, go like this, go skip, okay? Because we're gonna do this problem instead. We're gonna do an application problem instead. Put the application problem on a separate piece of paper, and you're gonna be handing this one in. So we're gonna get ahead on your homework for you instead of you having to do this one independently. Does that sound okay? We'll kind of kill 2 birds with 1 stone. We'll practice the process, but you'll also get to hand it in for a grade, okay? An easy 10 out of 10. So I'm gonna put this to the side. I'm gonna pull out a fresh piece of paper, and we are gonna draw our free body diagram. Our free body diagram is simply going to be a line. We're not going to draw any of these circles. It's going to be a line A to B. Okay, a line A to B. And then we're just going to draw the 4 vectors going down here. So I'm going to keep this up in case some of you don't have the handout like up or handy so that you can see. So I'm going to go zoom in maybe 2 more times. How's that? So this is problem 4.8. Oh, whoa, woohoo, can everyone else hear? Oh, can you not hear me? Sorry, my audio cut out. Yeah, we can hear. Thank you. It's back on now. Okay, good. Good. Now pull this down a little bit. Thank you, everybody, for communicating and answering. I really appreciate that. That's nice. I'll switch this out. Now, what's kind of nice about these problems is that we don't have to break anything in the components. We've got parallel forces. So all of our forces are going to be along the same line of action. So no components, which is kind of nice. That's a lot of times our step number 2. But instead, our step number 2, after we have our free body diagram, is going to be summing the forces to get our resultant. So what is the direction we're going to sum our forces in for this problem? What am I going to want to put right after my F here? A Y, yeah. So I'm going to do a Y. And then I'm going to go ahead and I'm going to sum my forces in that Y direction. So looking at the directions here, I've got a negative 0.5 kips, a negative 0.5 kips, a negative 0.5 kips, and a negative 1.5 kips is equal to my resultant. So I've got 1 plus 2, so that's negative 3 kips, right? Hold your negative. Now, if we go back to page 11 and we look at our process underneath here, we did our free body diagram. We determined our resultant. So step number 3 is we're going to determine the moment generated by the original forces. Okay, so our step number 3, it's going to be, we're going to sum our moments. Now, oh, I forgot to, this is point A and this is point B. Make sure you put all your points on. You probably did. And I'm going to sum my moments around point A. Okay, equal to. And I'm going to look at each one of my forces here that are going to cause rotation. So the first one is going to be my 1.5 kips, or I'm sorry, my 0.5 kips times perpendicular distance 4 feet. So 0.5 kips times 4 feet. And it is going to rotate in a clockwise direction. So we're going to put a negative out front. Then I'm going to do the next 0.5. It's going to cause rotation. So 0.5 kips times 8 feet. And it also is going to cause a clockwise rotation. So negative out front. And then the last force, it's going to be 1.5 kips times 12 feet. Okay. And it also is going to rotate clockwise, so negative out front for that one as well. William's got it already. Yay. That sounds like the right number. So if I take my moment around A and I multiply these out and add all the negatives, should get minus 24 kip feet. Excellent. And then just get a confirmation on that. Got it. Awesome. Thank you. Now, no box around that one because that's not a final answer. We did box the resultant because that's one of the things we're trying to find. But now we want to find that R bar. Okay, we want to find that R bar. So going back to that page 11 where we filled in, we're now going to set that moment that we just generated equal to the resultant times the R bar. Okay. So step number 4, it's going to be sum our moments around A equal to our resultant times our R bar. Now, again, what we want to do is we want to find out where are we going to place that resultant, like how far away from A? The reason we're using A is because that's where we summed around. If we summed around B, our distance would be from B. Okay. So now we're going to take that number and we're going to put that right there. The negative 24 kip feet. Keep your signs, remember. Equal to our resultant, negative 3 kips times R bar. So solving for R bar, negative 3 kips, cancel kips. We make top and bottom positive, feet are left for an R bar, and 24 divided by 3 is, I think it's 8, right? Oh, you got negative 20. Negative 20. Oh, let's check. James, you got negative 24, right? You got negative 24. Check one more time, Jack. 0.5 times 4, 0.5. Oh, Josh got negative 24. Make sure you've got the right distances. It's 4, 8, 12. Yep. Okay, good. Thank you. Thank you. Thank you. I'm glad you're checking though. Don't hesitate. If you get a different number, let's check it out. I'm going to be honest with you. I don't have an answer key in front of me. I do these right with you. And not that I get the answers wrong very often, but you know, you can hit the wrong button. I want us to do them together, right? Okay. So now we're going to, this should be 8 feet is equal to R bar. 8 feet is equal to R bar. Step number 5, what's one last thing that we want to do? Draw a diagram. Go ahead, draw a diagram. And make sure you do that all the time, all the time. So reviewing our process, things to make sure that you do. Number 1, free body diagram, all the labels, all the arrowheads, and your full convention. Then you're going to sum your forces in whatever direction they are. In this case, they're in the Y direction. That's going to equal our resultant. Using our up, down, left, right, being in force mode, if you would, then we were looking vertically. Anything that was up was positive, which were none. All of them were down, so we did negative. And then our moment, okay? That was going to be of the individual forces. And then we set that moment equal to the resultant times the R bar, with R bar being the only unknown. And then drawing our diagram. Diagrams are important for me because it's one thing to just do this process and get the numbers, but now I just want to make sure that you understand what those numbers mean. Okay. All right. So what I want to do is it's about 6:30. So why don't we take like a 10-minute break? Okay. It's 6:25 now. So at 6:35, we will resume and continue on.